In this video, we will discuss several more examples of power series and see if we can determine for which x's these power series converge. Very much like we did in example number 1, where we determined that this power series converges precisely when absolute value of x is less than 1. In the following example, number 3, we have to determine for which values of x is the series centered at 3 of this form convergent. So note that here we have series centered at 3 because we have x minus 3 to the k. So 3 here plays the role of a in this definition. Similarly, 1 over k here is the term corresponding to ck. So now in our series here we have a equals 3 and ck is equal to 1 over k, or k bigger than or equal to 1. C0, by the way, is simply 0 because there is no constant term. There is no term which does not involve a power of x minus 3. Okay. So to answer the question of this example, we will go ahead and apply the ratio test. Now, I should note that the ratio test is often the first tool you reach for when you're asked this question. If you're given a power series for which you want to determine which x's give you a convergent number series, the first thing to do is to apply the ratio test. So how would we do this? Well, recall that to apply the ratio test, we want to look at the ratio of ak plus 1 over ak. What is ak in our series? Well, ak is this entire expression. This entire thing is our ak, right? So let's put this here. Ak is the entire expression that corresponds to the index k. So we have x minus 3 to the k over 3. So, of course, in this case, this being a power series, our ak depends on x, and that is okay. So, in the ratio test, we look at the limit, k goes to infinity, ak plus 1 over ak under the absolute value, like so. For our specific ak's, this would be the limit, k goes to infinity, absolute value, then I have the term for ak plus 1, which is, whoops, I should have k here. So the ak plus 1 term is x minus 3 to the k plus 1 over k plus 1. I have replaced every occurrence of k with k plus 1. And this is divided by x minus 3 to the k over k. And this is the ak term. Once again, this entire expression corresponds to ak plus 1. And this here is nothing but ak. So this is the k plus first term of our power series. This is the kth term of our series. Great. So the first thing to observe is that there will be a lot of cancellation here, of course. All the powers of x minus 3 will cancel. So to see this massive cancellation coming, let us flip the second quotient first. We have limit k goes to infinity, x minus 3 to the k plus 1 over k plus 1 multiplied by k over x minus 3 to the k, everything under the absolute value. Okay, great. Now, what happens here is x minus 3 to the k is cancelled with this x minus 3 to the k, and we're only left with a single x minus 3 factor. This here becomes the limit as k goes to infinity, absolute value of x, let's put it this way, x minus 3 times k over k plus 1. Everything under the absolute value. Now, unlike it was in the case of number series, we must retain the absolute values here, because we do not know anything about the sign of x minus 3, right? It can be both positive and negative. We cannot tell this in advance, so we must keep the absolute values. What we can do, though, is to take this factor, which is positive, expression is positive here, we can take this outside of the absolute value sign. So we'll have limit k goes to infinity, k over k plus 1 times absolute value of x minus 3. So all we did was we factored out this positive expression from outside the absolute value. Now what happens to this limit, what happens to this expression in the limit k goes to infinity? Well, the only thing that depends on k is right here. This factor is completely independent of k. We may, in fact, just take it outside the limit. We can write it in this form. So this is independent of k, therefore, in terms of this limit, it is basically just a constant. We are taking the constant outside the limit. Right? Once again, x is independent of k, therefore this factor is effectively a constant with respect to k. And the limit is just k over k plus 1. This here is a simple limit. We compute it, and we see that this goes to 1. And so we ended up with the following expression. Now, let's see what this tells us about the series. We applied the ratio test, which told us to compute this limit. We went ahead and computed the limit, and we ended up with this expression. So now, according to the ratio test, here's what we can conclude. So the series is absolutely convergent when this expression is less than 1. So this is the conclusion of the ratio test. Furthermore, it is divergent when the expression that comes out of the ratio test is bigger than 1. This is also something that we know from the ratio test. If the expression that you compute in the ratio test is bigger than 1, then your series must be divergent. Finally, when absolute value of x minus 3 is precisely 1, as you know, the ratio test is inconclusive. So, what shall we do? Well, the answer to this is easy. We must consider this case separately. Since for all the other x's, we know what the behavior of this power series is, it remains to look at just the values that satisfy this relation. This is what we are now interested in. And this is what we will now study. Let's see what happens with our series when the absolute value of x minus 3 is precisely 1. So what are such values of x? Well, there are only two values of x which satisfy this relation. We have either x equal to 4 or x equals to 2. So these are the only x's which satisfy this relation. So what we will do is we will simply go ahead and plug these values of x into our series. We will obtain a number series, and for that number series, we will be able to answer if it is convergent or not. So for x equals 4, what do we see? Well, we started with the series that looked like so. For x equals 4, if we replace this x with 4, we will have a series that looks like this. Very nice, simple series. So this would be 4 minus 3, giving us 1 to the power k, which is just 1. So this is the resulting series. Now, we can say right away that this series here is divergent. It is a number series now, so we can apply all the familiar convergence tests to it, and in fact, it is divergent as a p-series, p equals 1. It's as easy as that. For this specific value x, our power series becomes simply this number series, which is a divergent p-series. So we can immediately answer if it is convergent or not. Likewise, for x equals to 2, here's what we have. Our series, the regional power series, which was this, becomes the sum of, okay, so here we have to replace x with 2. We have 2 minus 3, so that's minus 1 to the k divided by k. And this series here is, and I will let you think about it for a second. What can you say about this series? This series is convergent by the alternating series test. Okay, so what have we learned so far? We have a power series. We are trying to determine for which x it is convergent. First, by simply applying the ratio test, we're able to see that when absolute value x minus 3 is less than 1, this series is absolutely convergent. Similarly, we're able to see that it is divergent for such x's that x minus 3 absolute value is bigger than 1. And then we test the boundary conditions, the boundary cases, where x minus 3 absolute value is exactly 1. So we have the number line where we can show the value 3, right? And then these two cases are at equal distance from x equals 3. They are right here. So here is 2. Let's see, for 2 we are convergent. So let's this way. This is 2 and this is 4 here. And so our series is convergent for all x's that are over here and divergent everywhere else. So it is specifically convergent for x equals 2, right? Because as we tested, we got this conclusion here. And it is divergent for x equals 4. So we can write down our answer. This series is convergent for x in the half open interval from 2 to 4. We have to include 2 because for 2 x equals 2 our resulting number series is convergent, and we exclude 4 because as we tested right here, for x equals to 4 the resulting number series is divergent. And this is the answer to this question.